Hello everyone, welcome back to my channel. In this video, let us discuss about the topic called filters. So, a filter is a circuit that is capable of passing or amplifying the certain frequencies while stopping the other frequencies. Thus, a filter can extract important frequencies from signals that also contain undesirable or irrelevant frequencies. So, in the field of electronics, there are many particular applications for filter. For example, let us see these three examples. Filters are used in the radio communications, DC power supplies, and audio electronics. In radio communication, filters enable radio receivers to only see the desired signal while rejecting all other signals. Coming to the DC power supplies, filters are used to eliminate undesired high frequencies, that means noises. In audio electronics, filters are used to channel low frequency audios. So these filters can also be used in analog to digital conversions. That means these filters are placed in front of ADC input to minimize any other signals. Okay, next we have the four types of filters. Those are low pass filter, high pass filter, band pass filters, and band stop filters. So here the low pass filter means it only passes the low frequencies and stop high frequencies. And high pass filter means it only passes high pass frequencies and reject all low pass frequencies. And band pass filter means it only passes the frequencies which are on the sufficient band and they reject all the frequencies that are outside the band. And band stop filter means it stops all the frequencies that are on the edge of the band. So these are the four types of the important filters we have. And next, let us discuss about the importance of passive and active filters. So filters can be placed in the two categories. Those are called the passive or active. So these passive filters includes only passive components like resistors, capacitors, and inductors. And active components in active filters we have operational amplifier in additional to the resistors, capacitors, but not inductors. Sorry, in active filters we don't have inductors. So coming to the passive filters, those are most responsive to the frequency range from roughly 100 Hz to 300 megahertz. So the limitation on the lower end is a result of the fact that at low frequencies, the inductance or capacitance would have been quite large. So the upper frequency limit is due to the effect of capacitance and inductance. So coming to the active filters, these active filters are capable of dealing with very low frequencies. That means of approaching of 0 Hz, and they can provide voltage gain also. So these active filters can be used to design high order filters without the use of inductors. So this is the most important because inductors are problematic in the context of integrated circuit manufacturing techniques. So, however, these active filters are less suitable for high frequency applications because of amplifier bandwidth limitations. So, these radio frequency circuits must often utilize only passive filters only. So, next we have a Butterworth filter. So, this Butterworth filter is a so this is the Butterworth filter. Coming to this filter, mainly there are mainly three consideration in designing any filter circuit. So they have the response of the pass band must be the maximum flatness, and uh, there must be a slow transition from passband to the stop band, and the ability of the filter to pass signals without any distortions within the passband. So these three points are very important for any Butterworth filter. So coming to the Butterworth filter, at the expense of steepness in transition medium from passband to the stop band, this Butterworth filter will provide a flat response in the output signal. So it is also referred as maximally flat magnitude filter. Okay, the rate of fall off response of the filter is determined by the number of poles taken in the circuit. So the pole number will be depend on the number of the reactive elements in the circuit. that is the number of inductors or capacitors used in the circuit. So the amplitude response of nth Butterworth filter is given as this equation we have here. This is the equation for the nth Butterworth filter. So where n is the number of poles in the circuit, as the value of n increases, the flatness of the filter response also increases. So here F is a operating frequency of the circuit and Fc is the center frequency or cutoff frequency of the circuit. Okay, so these filters have predetermined considerations whose applications are mainly at active RC circuit uh, at high frequencies. Even though it does not provide the sharp cutoff response, it is often considered as the all-round filter which is used in many applications. So next we have coming next we have first order low pass Butterworth filter. So that is the circuit shown here is the first order low pass Butterworth filter. Okay. So the required passband gain of the Butterworth filter will mainly depends on the resistor value of R1 and RF, uh, where RF is nothing but the R2 here, and the cutoff frequency of the filter will depend on the R and C elements in this circuit. So the gain of the filter is given as so the gain of the filter will be as A max is equal to 1 plus R1 by RF. So the impedance of the capacitor is C and the voltage across the capacitor is given as the equation mentioned here. VC is equal to minus JXC by R minus JXC into VIN. So here where Xc is equal to 1 by 2 pi Fc, that is capacitive resistance. So the transfer function of the filter in the polar form is given as the equation below, where the gain of the filter will be V out by Vn is equal to A max by root over 1 plus F by Fh whole square, and the phase angle will be mentioned here, and the phase angle will be minus tan. This is the phase angle equation. So at low frequencies means when the operating frequency is lower than the cutoff frequency, then the passband is equal to the maximum gain. That means V out by VIN is equal to A maximum. This is the constant equation. So at high frequencies, which means the operating frequency is higher than the cutoff frequency, then the gain is less than the maximum. That means V out by Vin is equal to less than of A maximum. Okay, so when the operating frequency is equal to the cutoff frequency, the transfer function is equal to the A max by root over 2. That means the rate of decrease in the gain is 20 decibels by decade, or 6 decibels, and can be representative in the response slope as minus 20 decibels also. So next we have this topic called the second order Butterworth filter. So that is the circuit diagram of a second order Butterworth filter. So this is an additional RC network connected to the first order Butterworth filter, gives us a second order low pass filter. So this second order low pass filter has an advantage that the gain roll off very fast than the cutoff frequency in the stop band. So in this second order filter, the cutoff frequency value depends on the resistor and the capacitor values of two RC sections. So here the cutoff frequency is calculated by using this formula. Fc is equal to 1 by 2 pi root over R square into C square. So this is the topic for the second order low pass Butterworth filter. And coming to the applications of Butterworth filter, we have anti-aliasing filter, radars, and audio applications, and digital filters. In these are the applications which Butterworth filters are applied. So due to its maximum flat pass band nature, so it is used in anti-aliasing filter in data converter applications. And it has an applications in radars, such as in designing the display of the radar target attack. Okay, it also used in high quality audio applications, and also used in the digital filters also. So these are the applications of a Butterworth filter. Coming to the first order high pass Butterworth filter. So as mentioned earlier, a high pass filter is a circuit that attenuates, that means that stops all the signals and all the signals below a specified cutoff frequencies denoted as an F of L. So here the high pass filter performs the opposite function to that of the low pass filter. Okay, so hence the high pass first order Butterworth filter circuit can be obtained by interchanging frequency determining resistance and capacitors in a low pass circuit. So this is the circuit for the first order high pass Butterworth filter. So, so the first order high pass filter can be obtained by interchanging the elements R and C in the first order low pass circuit. Okay, so this is the circuit diagram of a Butterworth high pass filter. So it can be observed that as compared to the first order low pass, the positions of R and C are changed in the high pass circuit. So the frequency at which the gain of the filter passband is called the low pass frequency and is denoted by F of L. So all the frequencies greater than F of L are allowed to pass, but the maximum frequency which is allowed to pass is determined by the closed loop bandwidth of the op amp used. So coming to the analysis of this filter, here we have the impedance capacitance minus JXC is equal to minus J into 1 by 2 pi FC. By calculating this, sorry, here F is the input, that means operating frequency. By the voltage divider rule, the potential of non-inverting terminal of the operational amplifier will be VA is equal to V in into R by R minus J into XC. By further calculating this, we have this equation called J into 2 pi FC, where we have keep this the equation number 2. By substituting in the above expression of VA, we have we have this equation called VA is equal to V in into minus R by J into XC by minus R by J into XC plus 1. By further calculating this, we have the equation number 3. So this equation number 3 is represented as this equation VA is equal to VA in into J of F by FL by 1 plus J into F by FL. So here FL is the low cutoff frequency, which we have given as the equation number 4. So now for the operational amplifier in non-inverting configuration, we have V0 is equal to AF into VA, where VA is the voltage at the non-inverting input and AF is the gain of the op amp in the passband. Okay. So next we have the equation called V0 is equal to AF into VIN by J into F by FL by 1 plus J into F by FL. So by taking Vi out, we have the equation number 5. So this is the required expression for the transfer function of the filter. For the frequency response, we require the magnitude of the transfer function, which is given by V0 by Vn is equal to AF into F by FL into root over 1 plus F by FL whole square. So this is the equation 6, which is called the high pass filter. This is the behavior of the high pass filter. As we can see, this is the frequency response of the high pass Butterworth filter. Okay, next we have a band pass filter. So the band pass filter is a circuit which permits the signal to flow among two particular frequencies, although divides the signal at the other frequencies. So these filters are available in different types. Some of them are called band pass filter. Some of the band pass filter can be done with an external power as well as an active components such as integrated circuits transistors, which are named as an active band pass filter. So similarly, some of the filters use any kind of power source as well as a passive components like capacitors and inductors also, which are named as a passive bandpass filter. Okay, so these filters are applicable in wireless transmitters as well as receivers also. In transmitter, a bandpass filter can be used to limit the output signal bandwidth towards the minimum necessary level and transmitting data at the preferred speed and form. So similarly, in the receiver, the filters lets the signal in a favored frequency range to be decoded, whereas keeping away from the signals at unnecessary frequencies, the signal to the noise ratio of a receiver can be optimized by this bandpass filter. Okay, this is the circuit diagram for the bandpass filter. So here the bandpass filter is the RLC circuit. So this filter can also be designed by uniting the low pass filter and the high pass filter also. So uh, in this band pass filter, it is used to be differentiated from passband that refers to the real section of the influenced spectrum. So ideally, a bandpass filter doesn't have gain and attenuation. So it is totally a level passband. That means that will totally attenuate every frequencies exterior to the this pass band. Okay, this is the circuit diagram for the band pass filter. So here the band pass filter is not idle. That doesn't mean an attenuate every frequency is outside the preferred frequency choices. So particularly there is a section just outside to proposed pass band wherever these frequencies are stopped. However, these bandpass filters are specifically specified attenuation for every octave frequencies. So, in general, this filter bandwidth can be defined as upper frequencies as well as the lower frequencies also. So we have two types of bandpass filters. Those are called wide bandpass filter and a narrow bandpass filter. So these are the two types of bandpass filters. So in wide bandpass filter, uh, these wide bandpass filter can be formed by dropping low pass as well as high pass segments, which is normally a different circuit intended for a simple design and act. So this is the circuit diagram for band pass filter. It includes first order high pass and the first order low pass filter. So this is the circuit diagram for the band pass filter, and this is the frequency response for the band pass filter, wide band pass filter. As you can see, the frequency is in the wide, so that is called this is the wide band pass filter. So here it is a bandpass filter with high frequencies, first order high frequencies. This means the order of the bandpass filter is ruled with the order of low pass and the high pass filter. Okay, so this is the graph of this is the frequency response of the bandpass filter, wide bandpass filter. So here, next, we have the narrow bandpass filter. So generally, a narrow bandpass filter is used for several feedbacks. So this bandpass filter using an operational amplifier has shown here. So the main features are include mainly these 741 IC. So here we are using 741 IC for the narrow bandpass filter. So another name for this filter is called as a multi-feedback filter, and we have the frequency response here. We have the narrow bandwidth, so that is why it is called as a narrow bandpass filter. So the frequency here we have shown here is a narrow frequency. So next we have the topic called the band stop filter. So this band stop filter is formed when the low pass filter and the high pass filters are connected in parallel with each other. So the main function of this band stop filter is eliminating, that means it's stopping the particular band of frequencies. So the band filter is also referred with some other names like band reject or notch or band elimination filter also. So For high pass filter, there will be one cutoff frequency. Low pass filter also we have one cutoff frequency. But these band pass or band stop filters have two cutoff frequencies. Okay, so this is the frequency response of the band stop filter. So this frequency response of bandstop filter can be obtained by recording gain and frequencies. So this is the frequency response for the bandstop filter. So coming to the applications, uh, these bandstop filters are used in electronic guitar amplifiers and also in image and signal processing, reduction of static on a radio, and also used in the biomedical instrumentations. Biomedical instrumentations and public address systems, optical communication technologies, band stop filters can also be used to reduce unwanted harmonics and errors also. So coming to the last topic in this we have all pass filters. So this all pass filter is nothing but that means which passes all frequency components of the input signal without attenuation, but provides predictable phase shifts for the different frequencies of the input signal. So the all pass filters are also called as a decay equalizers or phase correctors also. So these an all pass filter with the output lagging behind the input is given in this in this response. As you can see, this it passes all frequencies. So here the output voltage V naught of the filter is shown here. So it can be obtained by using this superposition theorem. So here V out is equal to minus Vi in plus minus Jc by R minus J into Xc into 2 VIN. By substituting minus Jc is equal to 1 by J into 2 pi Fc in the above equation, we have the following equations. So this is the equation for the all pass filters. So this is for the today's topic. I hope you understand this topic.